So hi, everyone. I'm Alice Rixte, and I'm a PhD student at University of Bordeaux under the supervision of David Jana and Martin Laliberté. And today I would like to talk to you about generalizing turtle geometry and to show you a language that is extensible and that allows vector graphics drawing. And it does not work. So first I will try to show you what turtle geometry is, and then I will introduce you the Pandia language, which is a polymorphic language that allows to write multimedia domain-specific languages. Then I will show you the implementation of that language within Haskell. And to finish, I will show you how we can instantiate that language to vector graphics. So first, let me show you what turtle graphics is. So we have a little turtle. It's cute, right? It's heading north, and we can tell it, go forward, little turtle. And it goes forward. It behaves properly. And we can tell it to go left by 160 degrees. Nice. And to continue. And again. And now we're going to name this a squiggle because it is a squiggle. And we can ask it to do the squiggle twice, or 4 times, or 9 times. And after 36 times, the turtle is back to where it was at the beginning. And we have seen all the instructions we wanted to see, which is forward, left, or right, and repeat. Now, there are many extensions to turtle graphics. You can actually do images, but you can also do 3D and music. And in all these extensions, there are some common patterns. And those common patterns are the following. They all use some kind of primitive, like line segments for turtle graphics, or shapes for vector graphics. Those shapes are actually Bézier paths most of the time, meshes for 3D, or musical notes. And these primitives, we can draw them by traveling some kind of state. And this state can be either a space, or it can contain multiple dimensions, including 2D position or 3D position, orientation, rotation, scaling, stroke color, width, stroke width, and for music, it can be pitch, onset, duration, and you name it, any parameter can be in the state. Now, the dream would be, well, what if we can have one language to rule them all, obviously? And this is exactly what I'm trying to do in my PhD thesis. So that language, one language that does that is Pandia. And Pandia has only 4 instructions: the primitive instruction, the state change instruction, the state reset instruction, and the transformation instruction. The primitive instruction allows to render a primitive. So here we just tell the turtle to draw a circle where it is, which is at the origin, and this circle has by default a diameter of 1. The state change instruction tells the turtle to change its state. And here we tell the turtle to move right. So on the image of the left, you see the turtle moving right. And then on the image of the right, we add a second circle where the turtle went. Okay? We can use the repeat instruction from the turtle graphics language to do this 4 times, for instance. You notice that the turtle is 1 to the right to the last circle it drew. Now, the reset instruction allows to forget about any state change that happened within its scope. So here the scope is the whole program, actually, and we forget about the turtle moving to the right. So actually forgetting that means we are back to the origin. Now, if we add, after the reset, we tell the turtle to go up and then to draw a new circle. And now we have the following. Great. So can we do more? Yes, of course. We can repeat this 8 times and we get this square of circles. And this is possible thanks to the reset instruction. It has many more applications. For instance, here, I say the turtle to fill the shapes in gray, and I draw lines of circle, and I forget it with the reset instruction. And as you can see, I use the left, which is the rotation instruction, to outside of the reset part. And since it is outside of the reset part, it is not resetted, and we get this kind of wheel. And now for the last and fourth instruction, which is the transformation, what happens is that we can apply a transformation to each individual primitive that is within its scope. So for instance, here, the scope of the transformation is given by indentation, and we draw a line of circles that are all aligned. So we have 30 circles that are all aligned, and we apply a sinus function vertically to the position of each of the circles. Notice this is still Haskell. I'm using the overloaded dot extension. This is a field polymorphism. So you've seen all what Pandia can do, but we've seen like this very specific example. And now I would like to show you the polymorphic implementation, which can be specialized to any kind of media. So this is the monad that represents any media in the Pandia language. So the idea is that a media is a function that takes a state change, the current state, and returns some return value we do not care about, the rendered media, and the new state after having executed the media program. And we have our 4 instructions: the primitive instruction that takes a polymorphic primitive and returns a media, the change instruction that takes a state change and returns a media, the transformation instruction takes a state change, takes the scope of the transformation, which actually is a media, and returns a media, and the reset instruction takes the scope of the reset instruction, which is also a media, and returns a media. Now, how do we actually modify the state? Well, the obvious choice is to use state functions, which are functions from the state2 itself. But sometimes we only want to authorize a subset of those state changes. For instance, we can only want to have linear transformations. And actually, we can have a more general setting, which is to say that the state changes are a monoid, such that there is a monoid morphism from the monoid of state changes to the monoid of state functions. And this can be stated otherwise by simply saying that the state changes monoid acts on the states. So there are some laws. I'm not going to enter into the details. I hope some of you know a bit of algebra, and if you don't, it's okay. So knowing that the state changes act on the states, we can implement the change instruction by simply saying that we simply take the state change and it acts on the state. And it does not draw anything. This is the MMT here. This means we do not render anything. We are just modifying the state. The reset instruction only consists in executing the media that we received, discarding the new state, and returning the old state. along with the rendered media associated. The transformation instruction is just going to compose the current state change given in argument with the context. And we are going to use that context to implement primitive. But first, for the primitives, we need to know how to render a primitive, which means that we must have a function that takes the current state, takes a primitive, and returns a rendered media. So to implement a primitive, we take some polymorphic primitive. We use the render primitive function on the action of the current context, on the current state, and we feed it the current primitive. And as you notice, we do not modify the state. So change modifies the state without modifying the rendered media, whereas prim modifies the rendered media without modifying the state. So we have seen this very general kind of media monad. And now how can we instantiate it into a concrete domain-specific languages? Well, you're in luck, because actually we are going to do 3 of them in a few minutes. Turtle graphics, Bézier paths, and vector graphics. So for turtle graphics, the primitives are line segments. For Bézier paths, there are 2 primitives, anchor points and control points. And for vector graphics, we are going to take any Bézier path, and we can use either an open path or a closed path as a primitive. And here you can see actually 2 primitives, which are both closed paths. So which rendering monoid should we use? Well, for turtle graphics and vector graphics, we use superimposition. And for Bézier paths, we just use path concatenation. Actually, we just use list concatenation. So that's very simple to implement. The superimposition can be simple concatenation of strings, because I'm simply rendering to SVG. Now, how about the states? Well, for turtle graphics, we can use affine matrix, which will contain position and orientation of the turtle. We actually get more for free, like scaling, and whether the pen of the turtle is up or down. For Bézier path, we only keep the affine matrix. We do not care about the pen. And for vector graphics, we could actually add anything we want, but here we use fill color, stroke color, and stroke width. So today, for the sake of simplicity, I'm only going to use the state functions for state changes. And here, for instance, the rotation is a state change. We can implement it by simply multiplying a rotation matrix with the current state. But what's interesting here is that I use field polymorphism. And this means that this rotation state change is polymorphic in the state, as long as it has an affine field. And this is interesting, because if I want to implement the left and right instruction from the total graphics, well, then actually it remains polymorphic in the state. So we use the change instruction, and we use the state change we just defined, and we get left and right, and it is polymorphic in the state, which means that we can use these instructions with any media that has this affine field. And this means that any of the languages I just defined, which all had this affine field, as you remember here, can use the left and right instructions. So to finish, how do we instantiate correctly the media monad? Well, we feed it the change, an instantiation of the state changes, the states, the primitives. For turtle graphics, it will be segments and so on, and the rendering monoid. And since the monad I just showed you is actually a writer monad. We can execute it to get the final rendered meter. So for instance, we can implement an approximation of a circle by repeating 4 times the drawing of all these control and anchor points. But it gets better because we can use the code I just used before as a primitive to the vector graphics language. And we do that by simply saying, oh, we use that path as a closed Bézier path. And now we can use this circle syntactic sugar as monadic actions, which draw a circle. So here I say to the turtle, okay, now your state is fill red, stroke black, and you draw a circle. And then I say to move down and to fill in blue, and we get a square. And the square is defined the same way the circle is defined. So what to remember of this talk? Well, if you want to define a domain-specific language using this Pandia language with only 4 instructions, what you need is a rendering monoid, a set of states, a set of primitives whom you need to know how to render, and a set of a monoid of state changes that acts on the states. And if you have that, you will be able to define any kind of syntactic sugar to create your own domain-specific language. Now, if you have any suggestions, any ideas, or any questions, I would be happy to answer them. And thank you very much for your attention.
Yes, it was for specific. So I have a question. You showed examples with images. And also you showed that we can use circle in different domains, and how would like circles sound or
Yes, so in fact this is like just the beginning. I'm currently working on a real-time version of this. It's quite advanced, actually. In the case of music, well, basically here we have 3 different languages, and you can imagine that instead of, for instance, if you remember the states here, well, you could also put pitch and onset time and duration. And if you look at this rotation thing, well, you could write something like transpose. And this transpose thing would be, you could write some syntactic sugar with the transposition. So basically the turtle, instead of traveling a 2D space, it would simply travel more D space with pitch, duration, its onset time, and so on. And then if you know a bit of Haskell, well, you know that we have GHCI, and then this media thing can be actually put into the IO monad, and you get a REPL for free where you can play music. So this will be next year.
Just in the interest of time, I think we'll take any question. Well, one last question while Stephen gets up.
Okay, so my question is, so the code that you showed us, that is medium and that you implemented yourself, like go ahead with the code. But of course, a lot of these definitions you could get for free by using some library monads. Like I think if you read the writer state.
Yes. Yes.
So is there any reason that you're making your own from scratch instead of taking a stack of monad transformers?
Yes. Well, for first, stacking monads transformers is inefficient. So that's the main reason. And second, the thing is, sorry. Yes, the thing is, indeed, you can I get my, thank you. The thing is, you could actually define this, this is a reader monad, this is a state monad, and this is a writer monad. So you can make a monad stack transformer. But in fact, what I'm not saying is that all this is inside a class and in a MTL style. And it does not really matter since it's inside a class. So it's a good question, but I renamed those so that it also makes sense for what I want to do. Thank you for your question.
So that's all we have time for on questions. Thank you so much. I'll need to take that one.